So on Friday, I will give an extra lecture instead of the council lecture on Monday, and there will not be a lab on Friday. So only a lecture, which will be the last lecture of the course. We can arrange extra lab sessions if needed to answer questions. But then you have to agree with Sarvajit. Even if you have questions about the theory assignments, I can arrange some extra online lectures just to answer the questions. But I think I will go through the whole material today and finally on Friday. So this will be the last lecture, the last official lecture. The second theory assignment is available already, as you might know, and the same with the second code assignment, which is also available. The last theory and code assignments will be available next week, and the deadline will be sometime around the 10th of January. And there is the Slack space available, as I mentioned in the previous lecture. Okay, so what we did in the previous lecture was that we started looking at, in fact, we went through the lazy synchronization algorithm. So I will try to recall this algorithm today and then answer two questions that you asked last time. And then I will start with the Treiber stack algorithm today, hopefully. And then finally on Friday, I will go through the Michael and Scott Q algorithm. And I think this will conclude the course. So let's look at lazy synchronization. So we say that the goal of the algorithm was to achieve even more concurrency compared to previous versions of or previous algorithms that we went through to implement the set abstract data type. And the idea here was that to let the contain method avoid acquiring any locks. And we say that the motivation was that in a typical application, around 90% of the method calls will be contains, while the rest will be adds and receives. So this means that if you manage to make the contain operation efficient, then this means that you will increase the throughput of the algorithm, you will increase the concurrency, and you will increase the efficiency of the algorithm as a whole. And this is part of the second lab or the second assignment, code assignment. So hopefully you'll be able to observe this when you do your experiments. So then the goal is to increase concurrency. How? To let the contain method not acquire any locks. And then the strategy is to have a two-stage deletion procedure where we first logically delete the node. And then after having done that, so logical deletion means that you have a flag per node that you can set. It's a Boolean flag, and if you set it to true, then this indicates that the node has been logically deleted. So this means that when the other threads come and look at the cell, they know that it has been deleted, although it's physically still there. And then after that, after some time, the thread itself will delete the node physically. And this is done by redirecting the pointer of the cell pointed to by the so-called P pointer and let it point to the cell next to the cell pointed to by the C pointer, as we saw in the previous lectures and in the previous algorithms. So this is an overview or a high-level description of the lazy synchronization algorithm. And concretely, what we do is that we have the cell now, contains the key, it contains a flag which you call mark, which is either 0 or 1, true or false, where true means that it's a Boolean flag, and true means that it indicates whether the cell has been logically deleted. So true means that indeed the cell has been logically deleted. And false means that it's still there. So here what we do is that when we do the remove, we first delete logically, set the mark equal to 1, and then delete physically. And the contain method returns false, as we saw in the previous lecture, if either the node is logically deleted, so by checking the mark flag, or by concluding that the node with the right key is not there. Okay, and then the linearization policy was a bit more complicated, in fact. And already here we saw that although we are still dealing with the set abstract data type, which is one of the most trivial data structures in sequential programming, you see here it's not so clear. If you want, at least if you want to have efficiency, to guarantee the correctness of the algorithm, you have to provide a good linearization policy, and this can be complicated. So for the successful add, we say that the linearization point is the point when the P of next, or the next of the node pointed to by P is set to the node, which is the next of the cell pointed to by N. So now one question which was asked about assignment 2 was the following: what happens if two linearization points occur at the same point of time? And this is not possible because by assumption, we assume that a linearization point is a point. So this means that the linearization points themselves are considered as atomic events that cannot overlap. So given any two linearization points, one of them will occur before the other, although the respective methods may overlap. But this is the whole idea with linearization points, is that you choose or select a point of time during the interval of the call in which you assume that the call takes place or the method takes effect and will be visible to the rest of the threads. So at that point, for a successful adding, this algorithm is the point where we set P next to the next cell of the cell pointed to by N. For an unsuccessful add, it's that when you conclude that the key is there, and this is done by finding the cell with the right key. So this is physically there, but furthermore, it has not been deleted. So this means that the cell should be unmarked. In such a case, you will not succeed in adding the key again because it's already there. For a successful remove is that when it's the time of point when you logically delete the cell. That is the point of time where you mark the cell as deleted. So this is the linearization point for a successful remove. For an unsuccessful remove, it is that you find the first unmarked entry with a larger key. So this means that you find a cell inside the list, which has a key, which is there, which is inside the list, and which has a key which is larger than the given key, the input key. So in principle, this means that the key is not there, so you cannot remove it. A successful contain is that you find the key there, which means that you find the entry with the input key, but also provided that this entry is not marked. For unsuccessful contain, we say that the policy was a bit more complicated. And in fact, we first guessed a reasonable linearization policy, but we also showed a scenario which proved that this reasonable, what seemingly reasonable linearization policy is not correct. And then we proposed a correct linearization policy. So let's recall the example that we went through last time before I go to the questions that you asked in the previous lecture. So this was the example. So you see that we have the cells with key, mark, which is a Boolean flag, and lock. And then we have the linked list as usual. And then we have the locate procedure. And the locate procedure, what we say it does is that given a key, it looks inside the list and it checks whether the key is there and marked. If it is there, it will lock the previous cell and the current cell and then return pointers to these two cells. So in this particular example, we have these two, again, we have these two pointers, P and C, and then we start executing this while loop. until we find or we conclude that the key is not there. So in this case, this will be the case here because you execute this while loop, which means that this while loop here, the inner while loop, which means that you first start with P pointing to head and C always being the next of P, and then go through the while loop, searching for the correct key, whether it's there or not. And this means that you will search until your C pointer points to a cell or a node whose key is not strictly smaller than the input key, which is 4 here. And in such a case, you lock P and C, and then you check these conditions that the marks are false and that this pointer is still here. So this is the check that you do, and you see that these 3 conditions are satisfied because this mark is 0, this mark is 0, and this pointer of P is, or the next pointer of P is still pointing to C. And in such a case, you return these 2 pointers to the caller like this. A different scenario is that if this condition is not satisfied, so this means that when you do the while loop, you do find the correct cell, which is the first cell whose key is not strictly larger than 4, but you fail in testing, meaning that you have this mark, C mark is not 0. So this means that you repeat the loop. So this means that you unlock the cells. So this was the previous configuration. Because the test failed due to this mark being 1, means that you reset everything, unlock P, unlock C, which means that this if statement will fail. The condition here does not evaluate to true, it evaluates to false, which means that you unlock P and C and then repeat the loop. And this is what we are doing here. We are unlocking the 2 cells and then we are repeating the loop until we succeed. Okay, so then we say that now the add and the remove modules will use the locate as usual to find the right places inside the list where to search or where to look to see whether the key is there or not, and depending on that, whether adding or removing a node from the list. So for the case of a successful add, we are adding a 4 here in this case. So now what we do is that, so this will amount to a successful add. So we have this extra variable R in which we store the result. I mean, this is not necessary. This is just a different way of doing it. So you store the result true or false, which indicates the success of the operation in the variable R. So again, it's a Boolean flag, true or false. True means that the operation was successful. False means that the operation was not successful. And now I call the locate procedure, which means that it will find the right cell inside the list or the right 2 cells, lock them, and then return the pointers pointing to them. So this is what happens when you do the locate. So you see that you found the 2 cells, 5 and 3, where 5 is the first key in the cell, not strictly smaller than 4. Lock the 2 cells and return the pointers P and C to the caller. And this we did in detail in the previous lecture, so I'll not go through it again. So now you check whether the value of the cell point 2 by C, or the key in the cell point 2 by C, is equal or different from the input key, which is 4 in this case. Indeed, it's different, 5, which means that you will now execute these 3 lines here in which you create a new node with the new key. You call it N, and then you let the next of P to point to N, to the new node, and let the next of the new node N point to C. So this is what happens here. So this is what we did. We added the new cell with 4 as a key, which is the one to be added. And then we redirected the pointer of the P cell to point to the new node N, as we saw here. And we defined the pointer, the next pointer of the new cell to point to C, which is here. And as we say that for a successful add, the point of linearization is the point where we set the P next. So this is the point where we see where we set P next to point to n. So from now on, this cell is visible in the list, even physically. So this means that this is the point of time where this operation takes effect. So the second task is to define the value to return. And in this case, it should be true because the operation was successful. So this means that we set R to true, which is the result. And then when we return the value of R, which is true. And this means that the operation was successful. Now, if the add is not successful, you are trying to add a key 3, which is already in the list. Then what you do is that you do the locate as usual, lock the cells, get back the pointers. Now check the pointers, see whether the key of the C cell is equal or not to the input key, which is 3. In this case, they are equal. So this means that the add will fail, it will not be successful. And the linearization point is that when unmarked entry is observed. So it's exactly this point here. It's the linearization point because this is the point of time in which I find this entry, which is unmarked and equal to the input key. And what we do is that as a result, we return false. And this means that you return false because the operation was not successful. Like this. So this was the add method and its linearization policy. For remove, now what we said is that when we remove a node, we first logically remove the node by setting the mark flag to true before we physically remove the node by redirecting the next of the next pointer of the P cell. And this is an extra step compared to the previous algorithms, because in the previous algorithms, we removed the cell physically by just redirecting the next pointer of the P cell and making it point to the next, the node next to the cell pointed to by C. So in this case, we do the locate as usual. The locate will find the right place inside the list, locks the 2 cells and give me the pointers, which is these 2 pointers here. And now I come to the if statement to check whether I'll be successful or not. In this case, I'll be successful because the value of E is 3 and the value of C val is 3. So this means that I first do logical deletion. And when we do logical deletion, this will be also the linearization point, because the linearization point of successful remove is that when the cell is marked, which is equivalent to saying that the cell is logically deleted. So this is the logical deletion point. And this is done by setting mark to 1, which is what we do here. And now we are done with linearization. So this cell is not there anymore, although it's physically still existing inside the list, because if somebody comes and sets the list now, it will observe that some other thread has already removed the cell because it has set this flag to true. So now this will be the linearization point when the logical deletion takes place. And then now we proceed by doing the physical deletion by identifying the next of the cell C, which is N, and then redirecting P next to point to N, which is what we have done here. And now you see that the cell has been physically removed from the, okay, so let me see some question here. Chat. If I can make line 4 and 5 to be one atomic operation, do we need mark 4 and 5? Yes, in fact, we do need mark still. So this is just an optimization. This is what I believe anyway. Okay, so this is, I think you can come up with a counter example otherwise. And it will, this reminds me of your previous question, which I'll answer later today, in fact, or later in this lecture. So now we have defined the linearization point to be the point of logical deletion. And now we just unlock the cells as usual. We store the result in R, which is true in this case, and then return that result here, which is successful delete. For a unsuccessful remove or delete, we do the locate, but now you will observe that the key is not there. So this means that when you do the if statement, you conclude that this will be false. And this is the unsuccessful remove linearization point, first unmarked entry with larger key. So this is the point where we found the first node with a larger key and which is unmarked. And as I said, in fact, in the third assignment, I'll ask whether this word unmarked will be is needed or not. Anyway, so if this is the case, then you have failed with your removal, with the deletion. So you store the result in false, and you unlock the cells, and then you return the result. So let me see the chat. Okay, thanks. Go ahead. So the main feature of this algorithm is that the contain method does not need any locks. So what we do is that we just traverse the list until we find the appropriate place or the correct place. And we need only one pointer, which you call the current pointer C, which starts from head and goes through the list using the while loop as usual. So this is what happens. So if you do contain 3, you will appoint or assign C to the head of the list, and then you traverse the list, and then until you find the cell with the correct key, which is unmarked entry with input key found, and this will be a linearization point. And now the question from last lecture was that what happens if I read this and then after that somebody changes the mark, some other thread, and this I will answer later today. So if you observe the correct entry which is unmarked, then this will be the linearization point, and now you will succeed with this if statement because you have found the right key, and because B, which was assigned here, was false. Although at this point of time, when you are executing this if statement, the value of C mark may have changed, but it doesn't affect the correctness of the algorithm. So this is quite interesting. So once you have observed and you linearize at this point, then you are safe. If somebody comes later, after you have executed line number 4 and before you have executed line number 5, the result will still be true. So this the linearization point will be the correct one, and the result will still be true, and this will be the one that you return. And why this is the case, I will explain more in later today. Okay, so these were all the linearization policies for all the operations except for the unsuccessful contain, and then we said, okay, let's just follow this policy, and it's feasible to say that we assume the linearization point to be, for instance, the point, or at least one possibility to get a linearization point is to be the point where I find a cell to be marked. After all, if the cell is marked, then it has been logically deleted. So then it's logical or it's feasible to say that in such a case, I just say that I define my linearization point to be exactly the point where I conclude this, and then I return the result false. So now this is quite reasonable, but also as a proof that these algorithms are not easy to analyze, this turns out to be wrong. And we gave a scenario. Sorry for this in the previous lecture. In fact, to prove correctness of such algorithms, I mean, if you want to be really sure, either you do some kind of computer-aided verification. So either you use what's called theorem provers. Now, theorem provers are tools in which you can, in principle, edit or construct proofs manually, but in the form of a code, and the tool will check for you whether each step in your proof is correct. So this means that if you do the full proof, first you have to define, I mean, it's not trivial. So first you have to give it a model of the program, you have to formulate your linearization policy, and then you have to formulate the notion of linearizability, correctness. All these things you have to formulate logically. And once you have formulated all these things and you give proof rules, which should be sound, and you formulate them in the theorem prover, then you go on and do the proof in the theorem prover, and this will be like a certificate. The theorem prover will certify that your proof is correct. And in such a case, you can be reasonably sure that your linearization policy is the right one. Or you can do what we call model checking, which means that you construct another program which looks at your program and automatically checks whether it's linearizable or not. And both approaches are highly non-trivial. And in fact, we have worked with this in our research in Uppsala in previous years. Usually, the designer of the algorithm is supposed to provide the proof of correctness. Understandably, many of them will not do the full thing like theorem proving or model checking, but they give some arguments using informal like text or hand waving, if you wish, to argue for the correctness of the algorithm. And this is the usual thing that engineers do in practice. So what you do for the purposes of this course is that you look at the algorithm, you define or you consider different scenarios, and then you convince yourself that this algorithm is correct, or you find some error, perhaps, which has happened before. In fact, there are published algorithms with errors inside them, either in the algorithm itself or in the linearization policy. Okay, so here we have one example. So already at this simple level of sets, you can get such complicated scenarios. So suppose that this is our linearization policy, where we define it to be the point of time when we find a cell with the input key marked. And then we gave a counterexample, and the counterexample needed 3 threads. So first we started with contain 3. So now what we do is that it's contained, so we just go through the while loop without calling the locate or locking any cells. And we just find the right cell. And in this case, it will be the cell number with the key 3, so P and C. And this is what happens here. And now, just before we assign the value of C mark to be, the thread will become passive. So another thread will pop up, and it tries to remove the cell here. So if I describe the counterexample at a high level, what happens is that the red thread is looking for 3. Now 2 threads will pop up, one of them removing the 3 and the other one putting it back without the contain 3 being aware of this operation. So what happens is that remove 3 will come and it will call locate, which means that its 2 pointers will point to 1 and 3 respectively, and it locks these 2 cells like this. And then it checks whether this will be successful or not, and it will be successful because 3 is equal to 3, which means that when you come to the if statement here, you will set mark to 1, and this will be your linearization point. So you see that we say that the linearization point for successful remove was the point of time when the cell is marked, which is exactly here. So now we have linearized. And now we do the physical deletion of the cell. So first what we did was the logical deletion, which was the linearization point here. And now, as we say that, after the logical deletion, we perform physical deletion of the cell by redirecting this pointer to point to the next cell. And now we store the result, which is true, and then unlock the cells. So now this thread has terminated. So we indicate that in the figure here. And we indicate that the return result was true. So in other words, the red thread is still sleeping. The blue thread came along and removed the cell 3. Everything was fine. It was successful. It released the locks for the cells, and it terminated with a linearization point somewhere between, of course, the call and the return. So now 3 has been removed, but from the point of view of the red thread, it's still there. Now, suppose that a new thread will come and add 3 again. So this means that, again, what you do is that you do the locate. You look for the 2 relevant cells. So if you look at this list, these are the 2 relevant cells. The first one with the key which is not smaller than 3. So if you call locate there, add 3 has started now, and it will call locate, and this is what happens. So you lock the cells, and you get back the pointers pointing to the 2 cells, which is the first one with the key which is not smaller than 3, and the previous cell, or the predecessor in the list. So now you say that I succeed because, why? Because I'm trying to add 3 and 3 is not there. So the value of cval is 5, which is different from 3. And now we do as usual. You create a new cell, you redirect the pointer, the P pointer to the new cell, and the next of the new cell to point to C, and you linearize at the point where you redirect the next pointer of the P cell. So this is what happens. So this was the point at which we linearized, following our linearization policy for a successful add, sorry. And then after that, we record the result and we return the result, which is true. And now, it's only now that the red thread will become active again. It will check the C mark. So it looks at C mark, it says that it's true. So this means that B is true. This is the linearization point for it. And by our assumption, for an unsuccessful container, we say that we assume that the linearization point is the point where we find the key marked or logically deleted. So it says that the key is logically deleted. So exactly, this is the assumed linearization point, finding the cell with the input key marked. So this is the key with input key marked. So we return false. And now we have a history which is not linearizable. Because if you look at this history, we have removed 3, but we have added 3 again. But nevertheless, the contain method has returned a false. So this is not linearizable. So in fact, the history itself is linearizable, but the linearization policy that you have defined for the algorithm is wrong. So this means that, in fact, the algorithm is not wrong. It is, or at least it does not prove that the algorithm is wrong by itself, but it tells you that the linearization policy that you have defined is wrong. So in fact, a correct linearization policy, so this history as with the given linearization points is not linearizable, because the sequential history that you construct from this, which is unique, given the linearization points, this is not a history of the abstract data type set. So in fact, the correct linearization point is, or policy is that look at the interval of the red thread and look for one of these 3 conditions. Pick the earliest of these 3 conditions and define within the interval of the red, and define the linearization point to be exactly that point. And in fact, in the third assignment, I'll give you different scenarios where you have to apply these 3 conditions. So here, you see that the third condition will help us to avoid the bad scenario that you have in the previous slides. And the reason is that it says that, so the earliest point of time where we find the node key which is larger than input key, fine, this is logical. Or we find a marked node with key equal to input key, this is also fine. But also, you should take into consideration that you may find a point of time just before a new node has been added with key, which is equal to input key, which is what happened here. So we are trying to look for contain 3. Now, if I have within the interval of the red thread, which is going like this, so remember the red thread terminates after the green and the blue threads. So now here, this is the point of time where I have linearized the method, successfully adding the key 3 to the list. And then I take the time point exactly before that. So somewhere here, before this linearization point, and this gives me a linearizable history. Because now I remove 3, I contain 3, or I check for contain 3, it's not there. And then I add 3, which is fine. And again, I'll come back to this in the assignments and where you have to consider these conditions in more detail. Okay, so this is the linearization point which I defined just before the linearization point of a successful add with the same key. So now let's go to the scenarios that, other scenarios that help you to understand the algorithm even more. So the first scenario was a question by Ahmed, which said the following: suppose that we don't have logical deletion, only physical deletion. So what happens in such a case? Well, the simple answer is that it will not be linearizable. Let's see, give a scenario counter example for this. So if you don't have logical deletion, it means that you just forget about the mark. So this means that this one is not there, and you forget about the marks inside the cells, like this. So all these guys are not there. And also in the code, whenever you talk about mark, you just remove it. So let's see what happens in such a case. Let's see whether we can find a history which is not linearizable. So now I use 2 threads, the red thread and the blue thread for this. Let's see. So the red thread is trying to remove 5. So it starts by the locate. So the remove 5 is now active. It has issued a call. The red thread has issued a call, remove 5, and it will get some answer later and some linearization point according to a linearization policy. So now what happens is that we call the locate. And what the locate does is the following. First of all, we cannot use the mark because we are not allowing logical deletion. So this means that these 2 conditions will go, and the if statement will only check the pointer. And what it does is that it goes through the list using the while loop as usual. It just finds the correct cells, but then it goes to sleep. So now the red thread is sleeping, and we'll come back to it later. In the meantime, the blue thread will become active, and it tries to remove 3. And how it does that? Well, it's as usual. Again, something like that. Oh, sorry. So I don't have the mark, so I just remove it. Now the remove 3 will start working. So locate, remove 3 is active. And now call the locate procedure. What does it do? Well, it finds the correct cells, locks them, returns the 2 pointers. So this is the locate procedure as usual. Here, no marks. So you see that, no marks. here and here. So just checks the next pointer. So it goes through the while loop with these two pointers, and it finds the correct place, which is the first cell whose key is not smaller than the input key 3 there. And it checks this condition, it is fine. So it locks the cells. And then it checks the condition is fine, and then it returns the pointers. And now so no logical deletion, so just according to the proposal of Ahmed. So now N will be assigned C next. This is the next cell. And then we redirect the next pointer of the P cell and let it point to N, like this. And the result is true. And we unlock the cells as usual, and then we terminate, like this. So here, now I didn't even define the linearization point. You can take your linearization point to be anywhere in this interval, and the result will still be false, or the result will still be wrong. So now the blue thread has finished. So now it will become active again, the blue thread, and it tries to remove the 5, which will, in which it will be successful because the 5 is there. I will not go through the details of how it removes the 5. It's exactly the same way as it removed the 3. It's just that it starts to be active, and then it removes the 5, going through everything as we did in the case of 3, and it returns the value true. So now everything has finished, and now the red thread will become active again, and it's not aware that all these things have happened. So what it does is that it will check whether so it has done the while loop, and remember that the key for the for removal by the red thread is 5. So this means that it will check here, it has found the first cell, which is not strictly smaller than 5, which is the cell here. So now it will lock the cells, and then it returns the pointers P and C. And now it has done its job. So now the red thread is working. So if CVAL is true, so now it thinks that it has it will be successful because CVAL is equal to E. So CVAL is 5 and E is 5. So this if statement will evaluate, the condition of the if statement will evaluate false. So now this means that it will not logically delete because we don't have logical deletion. It just redirects the pointer. So it identifies the N cell, which is the next one, compared to the C cell, and it redirects the P pointer to point to N, like this. And then it says, yeah, I was successful. And then I log the cells and I return the result, which is true. And then I terminate. So now what happened is that we got this history here, which is not linearizable because we have removed 5. We succeeded in removing 5 twice without adding a 5, which is not correct, regardless of how you define your linearization point. So there is, in fact, this concurrent history is not linearizable in the first place. So this means that if you don't have, so you see the difference between this example and the previous example. In the previous example, the algorithm was correct, but the linearization policy that we proposed in the beginning was wrong. In this case, unfortunately, Ahmed's algorithm, I mean, I don't mean anything nasty, but the algorithm itself is wrong. So this is a concurrent history which is not linearizable, which means that regardless of where you find the linearization points, this will be wrong. But on the other hand, if you take the same example and you add back, so I will just talk 2 or 3 more minutes and then I will stop for the break. And you add back the mark, then everything will be fine. And the reason is that when the red thread now comes and tries to do the same thing, it will detect that this cell has these cells. In fact, both of them have been logically deleted. Because remember, the blue threads have physically deleted the cells, but before that, they have to logically delete the cells. So this means that when the red thread wakes up, it checks using the locate. Now it comes to this condition, it sees that this condition is not satisfied. In fact, both these conditions will fail because the marks are equal to true, which means that the negation is equal to false. And we know what this means is that we unlock the cells and then we go back and do the while loop again. And now we look for the cells again like this and find the correct cells, which will now be 1 and 7, because these are not part of the list again. So when you do the search through the while loop, the P will come here, but the C will go to the next cell, which is the C there. And then for the rest, it will go through, but now you return the value false because the key is not there. So what happens is that I'll not go through the continuation, but what will happen is that you do terminate, but you conclude that here, that the C val is not equal to E, which means that here, when you terminate, you have removed 5, but with the output result being false, which is 5. Okay, so this was the scenario. Now I will go through the next scenario. After the break, I'll go to the next scenario, which was a question asked by Gaulian, and also show why this is not correct. So I think these are very good questions. I encourage them very much. In fact, it allows me to think about some aspects of the algorithms which I may have missed before. And it also, these are nice questions. They are quite logical, they are quite natural. And it allows us to look, as I said, at different aspects of the algorithm, and it allows me to explain the algorithms more to you. So I very much encourage these questions. I think they are very good questions. Okay, so I will stop here, and if you have any questions, you can write them in the chat. I will try to answer them either after the break or by defining scenarios like that for the next lecture. And by the way, if you have questions regarding the assignments after the final lecture, you can also send them to me. Either I will answer them by mail or through Student Portalen and give copies to the PhD students, or if there are sufficiently many questions, I can have an extra session where I go through these online, where I go through the answers of the questions. Okay, so see you after the break.